If you've ever studied physics, you've probably heard of this book, i.e. Irodov's Problems in General Physics. Yeah, it's famous, or, maybe a little infamous, for its problems that really test your understanding. So today, we're going to tackle one of its classics. It's a problem that seems pretty simple on the surface, but the solution, it's just so elegant. Okay, let's dive right in.
So picture this. You're the captain of a spaceship, just cruising through the total emptiness of space. There's nothing out there to push against. No air, no water, nothing. So how in the world do you actually turn? I mean, this isn't just a fun sci-fi question. It's a real, fundamental physics puzzle that we're about to solve.
All right, let's get down to the specifics. We're going to look at the exact challenge that Irodov lays out for us.
And there it is, problem 1.181. Let's just break that down real quick. We're moving forward, we fire a thruster sideways, and we lose some mass, because, fuel. The whole goal is to figure out the final angle of our new flight path. Seems simple enough, right? Well, there's a little twist.
It always helps to get a picture of what's going on in your head. So imagine the spaceship is just humming along, let's call that the x-axis, with some starting velocity v0. Then, bam, the engine fires, creating this push at a perfect 90-degree angle that's along our y-axis, and it's this sideways push that's going to turn the ship.
Now, here's the most important part of this whole problem. This is the spot where so many people get tripped up on problems just like this one.
Look, in your very first physics class, you learned Newton's second law, F equals ma. It's beautiful, it's simple, and it works great for everyday things like pushing a box or a car. But our spaceship, it's spitting out fuel, so its mass is constantly going down. That m in F equals ma is changing. So that simple formula, it just won't work here. We're going to need a more powerful tool.
And lucky for us, physicists already figured this out. It's often called the Tsiolkovsky rocket equation, or more broadly, the equation for systems with variable mass.
This is our key. Let's just look at what's going on here. The left side, mass times acceleration, that looks pretty familiar. Over on the right, that F stands for any external forces. Think gravity or air resistance. But the new part, the really cool part, is that thrust term, U times dm dt. U is the speed of the gas being shot out relative to the ship, and dm dt is just the rate at which the ship is losing mass. This whole term is the force we get from shooting that mass out the back.
Now here's where things get a little easier for us. Remember, Irodov told us the spaceship is in the absence of external forces. So that means the F term in our big equation, it's just zero. Poof, gone. That simplifies things a whole lot. The only thing changing the ship's velocity is the thrust from its very own engine.
Okay, so we've got ourselves a two-dimensional problem here. The ship's moving forward and it's moving sideways. And the absolute best way to solve almost any 2D motion problem in physics is to just break it apart. We're going to treat the forward motion and the sideways motion like two separate, much easier, one-dimensional problems.
So here's our game plan. First, we'll look only at what's happening in that original forward direction. Then, we'll look at the new motion that the side thrusters are creating, and at the very end, we'll put it all back together.
Let's start with the easy part, that forward motion. Think about it. Are there any forces pushing or pulling the spaceship forwards or backwards? Nope. The thruster fired sideways. And since there's no force in the x direction, the velocity in that direction, Vx, doesn't change one bit. It just stays constant at its starting value, v0. See? Step 1, already done.
Now for the sideways motion. This is where all the action is happening. All that force from the thrust is pointed straight along the y-axis. So we're going to take our simplified rocket equation and apply it just to this direction to figure out how much sideways speed, Vy, we actually build up.
All right, time to roll up our sleeves and actually work through the math. Don't worry, we'll take it one step at a time. It's all very logical. Okay, so let's apply that rocket equation to the y direction. We've got m dvy divided by dt equals u dm divided by dt. In this equation, m is the ship's mass at any given moment, dvy is the tiny little bit of sideways speed it gains, and dm is the tiny bit of mass that gets ejected as fuel. We can just rearrange this a little to solve for that little change in velocity dvy. So, to find the total sideways velocity, we have to add up all of those tiny little changes, those dvy's, over the entire time the engine is firing. And in calculus, what's the fancy word for adding up tiny changes? It's integration. So we'll integrate from our starting mass, m0, all the way down to our final mass, m.
And this is what makes calculus so powerful. When we actually do that integration, we get this really beautiful, elegant result. The final sideways velocity Vy is simply the exhaust velocity u times the natural logarithm of the mass ratio, m0 over m. That's it. That's our final speed in the y direction.
We are so close. We have our final velocity components now. The forward velocity is still Vx equals V0, and we just found the sideways velocity Vy. So to find the final angle of our new path, all we have to do is combine them using a right-angle triangle. Basic trig tells us that the tangent of that angle, alpha, is just the opposite side, Vy, divided by the adjacent side, Vx.
And there we have it. The angle of deviation, alpha, is the arctangent of that whole expression. We have officially solved Irodov's spaceship problem. You can see how every single piece of information we were given in the original problem is right there in the final answer.
So what did we actually learn here? I mean, beyond just getting the answer to one tricky problem. Let's zoom out for a second and look at the big picture strategies we used. Honestly, this problem is a perfect masterclass in how to solve physics problems. First, we took a complicated 2D motion and we split it into simple, manageable, perpendicular parts. Second, we identified the real heart of the problem, that changing mass, and we picked the right tool for the job, the rocket equation. Third, we looked for a shortcut, and we found one by using conservation of momentum in the forward direction. And finally, we used calculus as the language to describe something that was changing continuously. These are strategies you can use in so many other physics problems.
And that pretty much brings us to the end. We've really mastered the basics here. But I'll leave you with one final thought to chew on. What if our spaceship wasn't in empty space? What if it was, say, orbiting a planet? How would that external force of gravity change our equation, and how would it change our final answer? Something to think about.